Good. Okay, thank you. So we showed for any function f of x that is differentiable of any order, and for any c, so c is in the domain of f. F of x can be written as nth derivative of f evaluated at c divided by n factorial times x minus c raised to the n, and from 0 to infinity. In fact, if you write first few terms, the first term is f at c, so just evaluate the function as c, plus f prime at c times x minus c. Then it's f double prime evaluated at c divided by 2 factorial x minus c squared, plus the next one is third derivative of f evaluated at c divided by 3 factorial times x minus c cubed, and so on. If c equals 0, by the way, c is called center, so c, as we mentioned, is the center of convergence interval. Okay. If c equals 0, then f of x becomes the nth derivative of f at 0 divided by n factorial times simply x, because x minus 0 is x to the n, and from 0 to infinity. This one, if you write down first few terms, that's simply f of 0 plus f prime at 0 times x plus f double prime at 0 2 factorial x squared plus so on. This one is called Maclaurin series. Okay. So Maclaurin series is a special case of Taylor series when c equals 0. All right. Okay. Now we're gonna find Maclaurin series or Taylor series for bunch of functions. Example. Write the Maclaurin series for e to the x. So my function is e to the x. Okay. First of all, what's derivative of e to the x is itself. Second derivative, same. Third derivative, same. So since any derivative of e to the x is e to the x, right? In fact, let me name it f of x, so makes it easier. Since f prime of x equals f double prime of x, and in general, any derivative of f is itself, and also, so let's write down Maclaurin series. That's what we ask. So what's the value of this function when x is 0? That's 1. So that the Maclaurin series e to the x equals to. So all the derivative, remember we're trying to apply this formula. So derivatives of f at 0 is 1 n factorial x to the n, and from 0 to infinity. Okay. And it's 1 plus x squared over 2 factorial x to the third over 3 factorial plus so on. So this guy is a Maclaurin series for e to the x. What's the radius of convergency of e to the x, of the power series of e to the x? Well, how does we figure out the radius of convergency? We call this, if we call this b sub n plus 1, b sub n, then we set up b sub n plus 1 over b sub n, took limit of that, set it equal, set it strictly less than 1 and solve for x, right? So in our case, it's going to be x to the n plus 1 factorial times n factorial x to the n. Limit of this as n approaches infinity. If you simplify it, you'll see it's x divided by n plus 1. In fact, we already found this. And that's 0, because x, is a finite value, n approaches infinity, that's 0. So no matter what, this is always strictly less than 1. That means, this means the summation of x to the n over n factorial, n from 0 to infinity, converges for all x's, real x's. In fact, the set of all real numbers is the interval of convergence, right? Negative infinity to infinity. So we don't have to worry about values that make it divergence. Let's find, okay. Let's do another one. So let's find the Taylor series for, sine of x. Let's call this f of x. All right. The first derivative is cosine of x. The second derivative is negative sine of x. The third derivative is negative cosine of x. The fourth derivative is sine of x again. So we went back to the original function, f of x. Now, fifth derivative, sixth derivative, seventh, eighth, and you can repeat this. So this order of derivative, in fact, dividing by 4, if you divide numbers divide by 4, the remainder is either 1, 2, 3, or 0. For that reason, that number can be represented as 4k, 4k plus 1, 4k plus 2, 4k plus 3. Okay? So any number, any natural number can be written as one of these guys. So the first one is a 4k plus 1 derivative of f of x. The next one is 4k plus 2 form of derivative. And then 4k plus 3. And this one is 4k. Okay. And we're going to evaluate them at 0. Okay. Remember, this is what we're trying to do. Sine of x is the nth derivative. So if you call this f, we're trying to find the nth derivative of f at 0 divided by n factorial x to the n. So what I'm trying to do here is finding the form or formula for that, for the nth derivative of sine at 0 and starting from 0 to infinity. So as you can see here, according to what we calculated above. What is the 4k plus 1 order derivative of sine at 0? Well, that's the derivative of all those terms. At 0 is 1. The 4k plus 2 derivative at 0, since it's negative sine, that's 0. 4k plus 3, that's negative 1. It's right here. And the 4k derivative is also 0. Right? So 2 of them are 0. In fact, if you notice, this index is even. This index is also even. Those ones are 0, but the odd ones, one is 1, the other one is negative 1. Okay? So, how do we figure this? How do we write this, as a formula? So let's see. If this is n, this is the nth derivative of 0. Nth derivative of f at 0. So 0, 1, 2. I'm trying to find a pattern. 4, 5, 6, 7, 8, 9. Okay? So the 0 derivative, we figured. Remember, this is 4k, 4k plus 1, 4k plus 2, 4k plus 3, 4k plus, it becomes 4k, 4k plus 1 again, 4k plus 2, 4k plus 3, 4k again, 4k plus 1. So those are all 0. The even ones are all 0. Okay? The odd ones, that one is 1. The negative 3, at 3, the third one is negative 1. 1, negative 1. 1. So for example, 10th one is 0, but the 11th one is negative 1. Well, it seems like odd ones, if we write them as 2k plus 1, this is simply negative 1 to the first. Right? This one is negative 1 to the second. This one is negative 1. Well, it's 2k minus 1. Negative 1 to the, oh damn it. Negative 1 to the third. That's negative 1 to the fourth. That's negative 1 to the fifth. That's negative 1 to the sixth. This 1, 2, 3, these guys are coming from the numbers that generate 11 as an odd number, right? 2 times 6 minus 1 is 11. 2 times 5 minus 1 is 9. 2 times 4 minus 1 is 7. 2 times 3 minus 1. So, seems like the f of 2k minus 1th derivative, okay, is negative 1 to the k. In fact, it doesn't matter if it's minus 1 plus 1. It's odd, so it would be the same. Okay, and all the even ones is 0. All right, now let's go to the Maclaurin series. So sine of x is the summation nth derivative of f at 0 and factorial x to the n. So if I split this up, I'll write down detail for this one. If you expand this f, as you remember, it's f of 0 plus f prime of 0, 1 factorial x plus f second derivative at 0, 2 factorial x squared plus. Split them up to even indices and odd indices. This is what I mean. f of 0 plus second derivative at 0, 2 factorial x squared plus fourth derivative of f at 0, 4 factorial plus. All right, now odd ones. So f prime at 0, x plus third derivative of f at 0, 3 factorial x cubed plus the next one is x to the fifth, x to the seventh. Now, based on what we found above, what's the value of that parenthesis, that giant parenthesis? It has all the even indices. Yeah, it's 0 because of this, right? We saw that all the even order derivative of f at 0, even order derivative of sine at 0 is simply 0. So this giant thing is 0. So, and by the way, you can see that this one can be written as f of, like, the 2kth derivative of f, where the index is even at 0, 2k factorial, k from 0 to infinity. And the other one, you can write it as all the odd indices. You can write it like this. I forgot x to the 2k. 2k plus 1 factorial, x to the 2k plus 1, k from 0 to infinity. So that's 0 for sine. The other one, we showed the numerator is negative 1 to the k, the rest itself, x to the 2k plus 1. And there you go. So sine of x, right, is, in fact, this is what we showed. The first derivative at 0 is 1, so that's 1. The second one was 0. The next one was negative 1, so it's negative 1 over 3 factorial x cubed. The fourth derivative is 0. The fifth one is positive 1 over 5 factorial x to the fifth. Then it's negative 7 factorial x to the 7th plus 1 over 9 factorial x to the 9th, and so on. The next one was negative. Okay? And this can be written as a summation. Here, k starts from 0. K from 0 to infinity. Negative 1 to the n, 2n plus 1 factorial x to the 2n plus 1, and from 0 to infinity. And by the way, here I'm using the variable of the series as k. I'm just changing it to n. It doesn't matter. They both generate the same thing, right? The sum of a sub n x to the n and sum of a sub k x to the k, k from 0 to infinity, and n from 0 to infinity. K from 0 to infinity. These two are the same. You're just changing that index, k to n. If someone used t, s, r, it would be the same. Doesn't matter what it is. Okay, so that was for sine of x. If you have your textbook and go to page 377, in the middle of the page, there are 5 power series for 5 elementary functions. The second one and third one, we found it, right? The first one, cosine, is a very similar process. In fact, for that one, all the odd indices derivative is 0. So that's why you have all the even indices, okay? So let me write that down. So cosine of x, so can be shown that cosine of x is the summation n from 0 to infinity, negative 1 to the n, 2n factorial x to the 2n. So if you open this, that's 1, minus x squared over 2 factorial. Oh guys, I made a mistake here. The first term here should be x. Right? Because if you go back, that's 0, but that one is not. So an f prime of 0 was 1, so it's 1 times x, which is x. Okay. So for cosine is 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6 over 6 factorial, and so on. All right. Now, by the way, someone could get this series. Someone could get this series by simply taking derivative of this one. So that 1 should be also x. No, this is 1. Remember, this is cosine. You know, that's the 0 order derivative of f at 0. That's an even order. That's an even, basically, order derivative. And we said, you know, it's not 0. In fact, what's cosine at 0? That's 1, right? In fact, this is nothing but cosine at 0. Remember, in any power series, the first term is f of 0 plus, you know, f prime of 0, x plus so on. So the first term is the value of the function at 0. So cosine of 0 is 1. That's where it's coming from. But what is sine of 0? Sine of 0 is 0, so that's why the first term is not 0. The first term is x. Okay? In fact, between sine and cosine, one function is even, the other one is odd. Right? In terms of, you know, symmetry with respect to y-axis and the origin. So which function is even and the other one is odd? Sine is odd, cosine is even. In fact, you can see that in the form of the Maclaurin series. Cosine is odd, cosine is even, and you can see the powers of all x's are even. So if you, you know, change it to negative x, you get the same thing. Whereas the powers of terms in the Maclaurin series of cosine is all odd, right? 1, 3, 5, 7, and so on. Okay. I'm going to write down, this one is easy. We know how to figure it out. I think I mentioned it. So consider the power series where a sub n is 1. In fact, consider this one. Right? We have 1 plus x squared plus x cubed plus x to the 4th, so on. We already know, you know, the sum of that series. In fact, we know what function it generates. Question 1. What kind of series is that? That type of series has name. That was the first type of series we even talked about in chapter 10. Yes, it's geometric. First of all, the rate here is x, right? So this power series is indeed a geometric series with ratio equal x. So the condition for convergency, so that we must have the absolute value of the ratio should be strictly less than 1. So for this power series, we have condition. Remember, for sine and cosine, if you find the interval of convergency, we see it's all R. Okay, so I'll write it here. Sine and cosine of x, Maclaurin series, converge everywhere. Okay. Whereas this one, no, we need restriction. X has to be strictly between 1 and -1. And if that happens, what's the summation? The first term divided by 1 minus ratio. So there you go. Basically, the power series, in fact, we could have started with this function and asked, what's the power series or Maclaurin series for that function? It's exactly this guy. Okay. So that's the fourth example that we're going to use as generating Maclaurin series. So 1 over 1 minus x Maclaurin series is sum of x to the n over from 0 to infinity, which is 1 plus x squared plus so on. Just make sure you mention that x, absolute value of x is less than 1, strictly. One thing you can do, you can, integrate, derive these power series, right? So, for example, integrate both sides. So if you integrate both sides, well, let's do this before that. If I change x to negative x, basically replace x with negative x, let's see what happens. We get 1 over. Let me write it here. We get 1 over 1 plus x. You okay with that? If you replace x with negative x, you're going to have negative x. So that becomes 1 over 1 plus x. Simply, you replace x with negative x to the n, and from 0 to infinity. And you can rewrite this as negative 1 to the n, x to the n. In fact, it's an alternating series, right? Terms are 1 minus x, plus x squared minus x cubed, right? Plus x to the fourth minus x to the fifth, and so on. So this one is the power series for 1 over 1 plus x. Condition is the same. Absolute value of x should be strictly less than 1. Integrate. If you integrate, what's the integration of 1 over 1 plus x? Has something to do with natural log of x. So it's natural log of 1 plus x equals antiderivative of that guy is the summation. Negative 1 to the n. Antiderivative of x to the n is x to the n plus 1 over n plus 1, and starting from 0 to infinity. And there you go. That's the power series for natural log of 1 plus x. Okay. Let's see. Let's find another one, another interesting function, power series. Basically, we can use power series to generate, power series for other familiar functions. So start with 1 over 1 minus x equals summation x to the n from 0 to infinity. Replace x with negative x squared. Let's see what happens. So if I do that, what do I get? I get 1 over 1 plus x squared, right? You replace x with negative x squared, that means you have negative x squared, which becomes that guy. Equals, you're replacing x with negative x squared, this is what you get. And from 0 to infinity. Which can be written, let me erase that. So, or 1 over 1 plus x squared is the summation negative 1 to the n, x to the 2n, and starting from 0 to infinity. Right? Now, this is not the one we care about. The integration of this one is an interesting one. What's antiderivative of that function? Tan inverse. Of x. An antiderivative of the series, well, the antiderivative of that is x to the 2n plus 1 over 2n plus 1. So we write that down. X to the 2n plus 1 over 2n plus 1, right? The power formula. And from 0 to infinity. So that's another power series formula. In fact, if you write down first few terms, tan inverse of negative x is. So first one is x. Okay. Then it's negative x cubed over 3 plus x to the 5th over 5 minus x to the 7th over 7 and so on. Now remember I said power series are used to approximate for approximation, especially for the approximation of irrational numbers. Here's an example. How do we approximate pi? Oops, pi. How much time do we have? 50 minutes left. Do you think we can survive with 10% left? We'll see. How do we approximate pi? Well, this is what you do. What is tan inverse of 1, guys? That's pi fourth, right? So this is what we can do. In power series, well, let me write down Maclaurin series, that's even more accurate. In Maclaurin series of tan inverse of x, let x be 1. Okay? If that happens, we get tan inverse of 1 equals to summation negative 1 to the n 1 raised to 2n plus 1 divided by 2n plus 1 and from 0 to infinity. 1 to the 2n plus 1 is 1, so we have simply negative 1 to the n over 2n plus 1 and from 0 to infinity. Question number 1, we need to make sure that this series converges. Question for you guys, does it converge or diverge, and why? Converges by alternating series test. Exactly. So it converges. Okay. But tan inverse of 1 is pi fourth. And so that's the summation of -1 to the n over 2n plus 1. That means pi fourth equals to, let's write down first few terms, n from 0 to infinity. It's going to be 1 minus 1/3 plus 1/5 minus 1/7 plus 1/9 minus 1 over 11, and so on. Now, if you wanted to solve for pi, you multiply both sides by 4. So pi is 4 times 1 minus 1/3 plus 1/5. And there you go. If this summation, can someone calculate it all the way through infinity, which is impossible, okay, then you can get as close as possible to the, to the value of pi. So here's a fact, very interesting fact. When you read an article where someone says, I don't know, this university or this professor or this researcher was able to find 2 millions of, digits of pi, or 1 billion or whatever, that guy is not doing a significant job is not doing something genius. Because the only thing he's doing, he is finding a machine, a computer, who is able to do this summation. So if you can't find a computer, supercomputer, that can, do this summation with as many as terms as possible, as many terms as possible, then you'll be a world genius. Simple as that. So that guy is not genius. The computer is doing the most of the job. His job is putting, pieces together so this computer can do this. And by the way, in your calculator, you don't even need these many terms. Probably what you need. Your calculator is only giving you this. It's giving you 4. Oops. Your calculator is only giving you this. 4 times 1 minus 1/3 plus 1/5 minus 1/7, I think plus 1/9. It ignores the rest. This is what you see in the calculator. That approximation, I think, is accurate up to probably 10th digit or 9th digit, whatever you need to fit in your calculator. So if it's a bigger one, if you can fit more digits, probably you can continue with 2 or 3 more terms, okay? And same thing for e, right? E to the x was summation of x to the n over n factorial, n from 0 to infinity, which is 1 plus x plus x over 2 factorial, x over 3 factorial, and so on. Now, to approximate e, all you have to do is let x be 1. So in that case, you get e equals 1 plus, in fact, another 1 plus 1/2 plus 1/6 plus 1 over 24 plus, 1 over 5 factorial, and so on. So the more you keep going in this summation, the more accurate you get to the actual value of e. But none of them can give you the exact value. All right. Any questions? Let's do some problems. Remember, in general, in fact, an obvious way to find Maclaurin series or Taylor series. Maclaurin or Taylor series we can find a pattern for nth derivative of f at x. As long as you can do that, we can find, in general, to find Maclaurin series, we can find a pattern for f, nth derivative of f at x, and then, because if you find that, you know f of x can be written as nth derivative of f at, for example, for Maclaurin at zeros, n factorial x to the n. That's what you do in a worst case scenario, okay? So, in fact, this is what I would say. Actually, let me just continue here. But using the Maclaurin series for elementary functions, for example, e to the x, e to the x, sine of x, cosine of x, right? 1 over 1 minus x, tan inverse of x, and all these guys. So using these, we can write Taylor and Maclaurin series for other functions, okay? But using Maclaurin series for elementary functions, we can come up with Maclaurin series for combinations of these functions. I'll explain it by a very simple example. Let's say you want to find the Maclaurin series for, 1 over 3 minus x. Okay? This is what we can do. We already know that 1 over 1 minus t, we already know Maclaurin series for that is sum of t to the n, and from 0 to infinity, right? The geometric series. We already know this. So if I can rewrite this function, if I can rewrite 1 over 3 minus x in this form, in fact, we don't care about the denominator if it's a constant. Let's go ahead and change that to, 5. So 5 over 3 minus x. 5 is a constant, so 5 over 3 minus x simply can be written as 5 times 1 over 3 minus x. So the 5 doesn't do anything. It's not significant. What I care about is that I would like to write this guy in this form, 1 over 1 minus something, right? maybe a scalar, or you factor something, right? To write it in that form. In fact, to be more precise, I already have the 5 times 1 over in the numerator. So I'm going to write this as 1 minus, okay. So what I care about, instead of 3, I want the first term to be 1. So what should I do? In the denominator. You have 3 minus x. Yeah, exactly. That means you factor 3. So if you factor 3, you get 1 minus x over 3. So that's the factor of 3. And then you have x over 3 right there. Those two are the same. Now it's ready to apply the Maclaurin series 4. Okay, so this is 5/3. Okay, now according to this, it's like you're letting t be x over 3. So this is summation. So here we have 5 over 3 minus x. It's 5/3 summation. Summation of t to the n, but t is x over 3 to the n, and from 0 to infinity. And right away we can figure out what the interval of convergency. Well, this is a geometric series with ratio x over 3, so that has to be strictly less than 1. That means absolute value of x should be strictly less than 3, or x between -3 and 3. Okay, and so that's it. That means 5 over 3 minus x Maclaurin series is 5/3 summation of x to the n over 3 to the n from 0 to infinity. And if someone is interested, you can write down, terms to see what it looks like. So it's 1 plus x third plus x squared over 9 plus x cubed over 27, so on. Okay? Question on that? Let me do one more example. This one is very quick. This is part D of question 2. You want to write down Maclaurin series for cosine square of x. Let me give you a hint. We have the Maclaurin series for cosine of x, or cosine of whatever argument. But here you have cosine square of x. So first you want to figure out if there's an identity they can relate second power of cosine to maybe first power of cosine. Is there one? Yeah, exactly. That's what we do. So using half angle formula, this is 1 plus cosine of 2x over 2. Or indeed, it's half plus half cosine of 2x. Well, we know the Maclaurin series for that one. That's half plus half. All right. So if you can recall, it was -1 to the n, 2n factorial, and then argument raised to 2n. Well, the argument is here is 2x. And I can rewrite it. So cosine square of x is half plus half times -1 to the n. If you want, you can rewrite this as 2 to the 2n, x to the 2n. And that one is 4 to the n. So that's 4 to the n, x to the 2n, and 2n factorial. Okay. So that's the Maclaurin series for cosine square of x. So, you can manipulate these functions to put them in the form of those elementary functions we already, and then use those. Okay? And that's it, guys. Problems are posted. They're doable. Work on them for today and tomorrow, and you can ask, for Thursday and Friday. Friday review session, Thursday is quiz review for the quiz level. Any questions? Also, do me a favor and evaluation form for the instructor of a good WMU. And if